A spiral galaxy spins in the quiet dark, beautiful and familiar. Now pull back, faster and farther, until that whole galaxy is just a speck of dust. Pull back further still, and a monstrous shape swims into view. This is no ordinary galaxy. This is the Godzilla Galaxy, a cosmic anomaly so vast and ancient it breaks the rules of the universe. Officially called Mammoth 1, this isn't just a new discovery. It's a profound mystery that challenges everything we think we know about how the cosmos grows. By the end of this, you will understand how a single distant smudge of light is forcing scientists to question the foundational laws of the universe. How did a structure this colossal form when the universe itself was just a toddler? And what does its existence say about the hidden skeleton of reality? When you look up at the night sky, how much do you truly believe we understand? Its official name is Mammoth 1, a designation that feels almost too modest for what it represents. Found in a region of space so distant its light has been traveling for over 10 billion years to reach us, this object is not a single galaxy. It is something far more immense and primordial. Mammoth 1 is a galaxy cluster protocluster. Think of it not as a finished city, but as the raw scaffolding, the frantic construction site for a future metropolis of galaxies. At its heart lies a supermassive black hole, a raging quasar, and around it swirls an ocean of gas so vast it could birth more than 10 trillion stars like our own sun. The scale is incomprehensible. Our entire Milky Way galaxy, with its hundreds of billions of stars, is a mere village compared to this emerging cosmic capital. This is why it earned the nickname the Godzilla Galaxy. It is a monster in every sense, a titan that stomps through the early universe, leaving theoretical wreckage in its wake. Spotting such a behemoth required a new kind of cosmic detective work. Teams of astronomers using powerful instruments like the Atacama Large Millimeter Array, or ALMA, in Chile, and the Subaru Telescope in Hawaii had to piece together clues from faint whispers of light that began their journey when the universe was only about 3 billion years old. They weren't just looking for a galaxy, they were looking for the shadow of a giant. And what they found did not just surprise them, it contradicted the very blueprints we have for how the universe builds its largest structures. This discovery presents a timeline that simply does not add up. We are seeing the Godzilla Galaxy not as it is today, but as it was when the light first left it over 10 billion years ago. At that moment, the universe itself was a mere toddler, only about 2 or 3 billion years old. And according to our most trusted models of cosmic evolution, that is far, far too early for something of this scale to exist. Think of the universe after the Big Bang as a vast, nearly smooth soup of matter and energy. The recipe for everything we see today, from stars to superclusters, begins with tiny ripples in that primordial soup. Over eons, the relentless pull of gravity acts on those ripples. Denser patches attract more matter, slowly growing into the first stars. Those stars gather into the first small, fragile galaxies. Only after much more time do those galaxies themselves begin to merge and cluster together, eventually forming the immense galactic cities we see in the modern universe. It is a gradual, bottom-up process, a cosmic assembly line that takes billions upon billions of years. Mammoth 1 shatters that timeline. It is not a single young galaxy. It is the bustling, half-built core of a future galaxy cluster, a structure that by all rights should not have had the time to gather so much material. Finding it in the early universe is the archaeological equivalent of excavating the foundation of a modern skyscraper, and discovering it was laid down during the Stone Age. The tools and the timeline are completely mismatched. This forces a haunting question upon cosmologists. If our understanding of gravity and cosmic growth is correct, then how did this titan build itself so quickly? The true shock of the Godzilla Galaxy only becomes clear when you see what it is connected to. This titan is not a lonely monster in the void. It is, in fact, the brightest beacon in something far more colossal and unsettling. Astronomers mapping its region of the early universe have found that Mammoth 1 sits along a structure they call the Giant Arc, a filament of galaxies, gas, and dark matter that stretches an almost unimaginable 3.3 billion light-years across the cosmos. To grasp that scale, try this. The distance from one end of this arc to the other is about 1/15 the radius of the entire observable universe. And we are seeing it from a time when the cosmos was only a quarter of its current age. This is not just a big thing. It is a structural beam in the infant universe, a backbone of reality that by all our models should not have had the time to form. The giant arc is a pattern, a vast, coherent shape written across the sky, and patterns of that scale strike at the very heart of a foundational rule in cosmology, something called the cosmological principle. This principle is a simple but powerful assumption that the universe, when viewed on the largest scales, is homogeneous and isotropic. In plain language, that means it should look roughly the same in all directions, and no one place should be too special. It is the idea that the cosmos is like a well-mixed batter, with no gigantic lumps or threads that stand out from the rest. The giant arc, with the Godzilla Galaxy as its shining jewel, is the opposite of that. It is a colossal lump, a thread so vast it seems to violate the rule. Together, these discoveries paint a picture of an early universe that was not a smooth, featureless soup, but was instead shockingly textured, lumpy, and structured far earlier than anyone predicted. It suggests the seeds of cosmic structure were planted with a force and a pattern we do not yet understand. If the universe's batter was this lumpy so soon after mixing, what does that say about the recipe itself? The immense size of this cosmic structure is not its only bizarre feature. The Godzilla Galaxy possesses a ghostly, luminous aura that marks it as something truly rare and strange. It is classified as an extreme Lyman alpha blob. To understand what that means, picture not the sharp, bright points of stars, but a vast, diffuse cloud of primordial hydrogen gas glowing with a faint, specific ultraviolet light. This is a Lyman alpha blob, and Mammoth 1 is one of the largest and brightest ever witnessed. That faint glow is a cosmic fingerprint, the specific signature given off when hydrogen gas is energized. But the sheer scale of this glow around the Godzilla Galaxy presents a profound mystery. What possible engine could be powerful enough to light up a gas cloud that spans hundreds of thousands of light years? Scientists are faced with three leading suspects, each more violent than the last. The first is a frenzy of star formation on an almost unimaginable scale. A stellar nursery so intense its collective ultraviolet radiation sets the entire surrounding nebula ablaze with light. The second is the furious activity of the supermassive black hole at the galaxy's heart, its quasars spewing out unimaginable energy that ripples through the gas like a shockwave. The third, and perhaps most intriguing, is a process called cold gas accretion, where rivers of pristine, cold hydrogen from the cosmic web are funneling directly into the galaxy, crashing down and glowing from the sheer violence of the infall. This glowing halo is not just a decoration, it is a key piece of the puzzle. It is the visible sign of a system in extreme turmoil, a titan feeding and growing through processes so energetic they defy our expectations for such an early epoch. The light we see is the echo of a cosmic tantrum, and we are still trying to understand what is throwing it. That faint, glowing halo might be the key to its impossible size. To understand how the Godzilla Galaxy grew into a titan while the universe was still young, we need to look at the hidden architecture of the cosmos itself. Picture the universe not as empty space dotted with galaxies, but as a vast, three-dimensional spiderweb. This is the cosmic web, the fundamental skeleton of reality. Its threads are made of dark matter, an invisible substance that exerts a powerful gravitational pull. Along these dark matter filaments flow rivers of ordinary hydrogen gas, the raw fuel for building stars and galaxies. Where these filaments cross and knot together, you find the densest hubs of matter in the universe. These are the nexuses where future galaxy clusters are born. The leading hypothesis is that Mammoth 1 did not just get lucky. It hit the cosmic jackpot. It sits at a rare, ultra-dense intersection of multiple major filaments in the cosmic web. Think of it as a drain sitting at the precise point where several massive watersheds converge. From all directions, colossal rivers of cold, primordial gas are funneled directly into its core. This gives the galaxy and its central black hole a nearly limitless buffet of building material, allowing it to feast and grow at a breakneck pace that defies the standard, slower models of cosmic evolution. It didn't just grow on its own, it was force-fed by the very structure of the infant universe. This scenario would explain the galaxy's extreme luminosity, its rapid star formation, and its shocking maturity. It was built not from the ground up, but from the web in. But a cosmic drainpipe is only one part of the story. To truly power the Godzilla Galaxy's furious glow, you need an engine, a powerhouse of almost unimaginable violence. That engine likely lies at its very heart, a supermassive black hole in the midst of a cosmic feast. This is not a dormant giant, but a quasar, a black hole so actively devouring matter that it becomes the brightest object in its region of the universe. As vast rivers of gas spiral down into its gravitational well, they don't just vanish quietly. They collide, they compress, and they heat up to millions of degrees, forming a swirling, luminous disk of doomed material. This process unleashes a torrent of high-energy radiation across the entire electromagnetic spectrum, from X-rays to ultraviolet light. It is this ferocious ultraviolet light that may be the true artist behind the galaxy's immense glowing halo. Imagine the quasar not as a dark pit, but as a brilliant, searing lighthouse. Its intense beam of energy floods the surrounding ocean of hydrogen gas. This radiation strips electrons from the hydrogen atoms, a process called ionization, and then, as those electrons recombine with the atoms, they emit that specific, telltale Lyman alpha glow we observe across hundreds of thousands of light years. The quasar, in essence, is painting the sky with its own waste light, illuminating the very gas cloud that feeds it. To produce an aurora of that scale, however, this black hole would need to be a true monster in its own right. Based on the energy required, astronomers estimate the black hole at the core of Mammoth 1 could have a mass exceeding 1 billion times that of our Sun. And here, the mystery deepens from one of structure to one of time. Forming a black hole that colossal, that quickly, is a staggering challenge. Our current models for black hole growth involve gradual feeding and mergers over billions of years. To find a billion solar, mass behemoth shining brightly when the universe was barely 1 billion years old means it had to start growing almost immediately after the first stars flickered to life. It forces us to ask whether the first seeds of supermassive black holes were far larger than we thought, or whether there existed some exotic, hyper-efficient method of feeding in the early cosmos that we have not yet dreamed of. The Godzilla Galaxy is not just a structural anomaly, it contains a temporal paradox at its very center, a hungry ghost that grew up far too fast. This leaves us with a profound and unsettling question. Does the Godzilla Galaxy simply point to a gap in our knowledge, or does it reveal a crack in the very foundation of modern cosmology? To understand the weight of this discovery, we need to meet the reigning theory of the universe, the framework that has guided our understanding for decades. It is called the Lambda Cold Dark Matter Model, or Lambda CDM for short. Think of it as the instruction manual for the cosmos, our best attempt to write down the rules that govern everything from the first spark of the Big Bang to the vast galactic structures we see today. This model is built on a few key pillars. It tells us the universe is made of roughly 5% ordinary matter, the stuff of stars, planets, and us. About 27% is cold dark matter, the invisible gravitational glue that holds galaxies together, and a whopping 68% is dark energy, a mysterious force causing the expansion of the universe to accelerate. Lambda CDM also makes very specific predictions about how structure forms. It says the universe started nearly smooth with only tiny ripples in density. Gravity worked slowly on these ripples, pulling matter together in a gradual, bottom-up process. First came small clumps, then dwarf galaxies, then larger galaxies, and only after many billions of years did the largest clusters and superclusters assemble. It also enforces the cosmological principle, the idea that on the largest scales, the universe is uniform and has no preferred direction. For a long time, this model has been remarkably successful, explaining a wide array of observations from the cosmic microwave background to the distribution of galaxies. But the Godzilla Galaxy and the giant arc are not playing by this instruction manual. They are throwing it into question. Finding a protocluster as massive as Mammoth 1 in the early universe is like finding a fully grown oak tree in a forest of saplings that are only a few years old. The timeline is all wrong, and the giant arc, a coherent structure spanning billions of light years, directly challenges the expectation of large-scale uniformity. It is not a minor statistical fluke. It is a glaring architectural feature in a universe that is supposed to look like a featureless expanse when you zoom out far enough. So what does this mean for Lambda CDM? Scientists are faced with two equally revolutionary possibilities. The first is that our understanding of the model's ingredients, particularly dark matter and dark energy, is flawed or incomplete. Perhaps dark matter is not perfectly cold, but has some subtle properties that allowed structures to form faster. Maybe the influence of dark energy in the early universe was different than we assume. The second, even more radical idea is that the seeds of the universe were not the tiny, gentle ripples we have always assumed. Instead, the initial conditions of the cosmos may have contained much larger density fluctuations, gigantic primordial mountains and valleys in the fabric of spacetime that collapsed into colossal structures almost immediately. This would be a fundamental rewrite of the universe's opening chapter. The Godzilla Galaxy is not just an oddity, it is a potential messenger telling us that our standard model, as elegant and successful as it has been, might be missing a crucial piece of the story. The mystery of this cosmic titan would remain forever hidden if not for a revolution in how we see the universe. To find the Godzilla Galaxy, astronomers had to move beyond capturing simple pictures of starlight. They needed to learn how to see the invisible, to map the cold, dark building blocks of reality itself. This feat was accomplished by one of the most sophisticated machines ever built by humanity, perched on a high, dry plateau in the Chilean Andes. The Atacama Large Millimeter/Submillimeter Array, known as ALMA, is not a single telescope, but a symphony of 66 high-precision antennas working in concert. These dishes are tuned not to visible light, but to much longer wavelengths in the millimeter and submillimeter range. Why does this matter? Because the universe's most important construction material, the vast reservoirs of cold molecular gas and dust that collapse to form stars and galaxies, is largely dark to optical telescopes. It hides in the shadows, but this cold material naturally glows with a faint, specific warmth at these longer wavelengths. ALMA is essentially a radio camera designed to see the cold. It can detect the faint thermal whisper of gas clouds only a few tens of degrees above absolute zero, revealing the hidden skeleton of cosmic structure. When pointed at the patch of sky containing Mammoth 1, ALMA did not see a brilliant pinprick of stars. Instead, it saw a colossal, swirling smudge of emission, a map of the unimaginable cold gas reservoir fueling the galaxy's monstrous growth. This was the first direct image of the Godzilla Galaxy's true body, a body made of potential. But seeing the gas was only the first step. The next crucial piece of the puzzle was determining just how far away, and therefore how old, this structure truly was. For this, astronomers turned to a powerful technique called spectroscopy. They used instruments on telescopes like the Subaru telescope in Hawaii to capture the light from the bright quasar at the galaxy's heart and from its glowing halo. They then spread that light out into a rainbow, a spectrum, and searched for specific chemical fingerprints. The key fingerprint they looked for is an absorption line from hydrogen known as the Lyman alpha line. Here is where a fundamental feature of our expanding universe comes into play. As light travels across the cosmos for billions of years, the space through which it moves is itself stretching. This stretches the light waves, making them longer and shifting them toward the red end of the spectrum, a phenomenon aptly called redshift. The greater the redshift, the longer the light has been traveling, and the farther away and older the object is. The spectrum from Mammoth 1 showed a Lyman alpha line that was dramatically redshifted. By measuring exactly how much that familiar fingerprint had been stretched, scientists could calculate the distance with extraordinary precision. The answer was staggering. The light had been journeying for over 10 billion years. This single measurement transformed the discovery from a curious, fuzzy blob into a confirmed relic from the universe's youth, locking in the impossible timeline that makes it so revolutionary. ALMA capabilities went even further. It didn't just take a static picture of the gas, it could also analyze its motion. Using the subtle shifts in the wavelength of light emitted by specific molecules within the gas cloud, astronomers could map the velocity and distribution of the material. They could see how fast the gas was swirling, whether it was flowing inward or outward, and trace the dynamic currents within the Titan. This data is what allowed them to piece together the scenario of the cosmic drainpipe, the funneling of cold gas from the web into the galaxy's core. It revealed a system in violent, chaotic motion, a feeding frenzy on a cosmic scale. Every piece of data, from the redshift confirming its ancient age to the velocity maps of its churning heart, was a testament to human ingenuity. We built machines to see the unseen, devised theories to interpret faint whispers of radiation, and patiently assembled a portrait of a monster from the dawn of time. The Godzilla Galaxy is not just a challenge to our theories, it is a triumph of our curiosity, a reminder that the universe's greatest secrets yield not to a casual glance, but to the relentless, clever gaze of science. Yet for all its startling implications, this discovery must first pass the gauntlet of scientific skepticism. After all, the history of astronomy is filled with tantalizing patterns that later dissolved under closer scrutiny. Could the giant arc, that colossal filament stretching 3.3 billion light-years, simply be a trick of perspective? This is the crucial question posed by cautious researchers. They argue that when you look deep enough into the cosmos, you are bound to find apparent alignments of galaxies and gas clouds that are not physically connected at all. They are just unrelated structures that happen to lie along the same line of sight from our vantage point, like distant mountains that appear to form a single ridge when viewed from a specific valley. If true, it would mean the Godzilla Galaxy is still a monstrous anomaly, but the overarching architecture of the giant arc would be an illusion, a statistical fluke in a vast and crowded sky. This possibility forces the team behind the discovery to run rigorous probability tests. They must calculate the odds that so many luminous quasars, gas clouds, and young galaxies would randomly line up in such a coherent, curved structure purely by chance. The initial calculations suggest those odds are vanishingly small, less than 1%. But in cosmology, even a 1 in 100 chance cannot be dismissed outright, and other teams are now performing their own analyses to either confirm or refute the structure's reality. Skepticism also extends to the data itself. The measurements of distance, those critical redshifts that tell us how old these objects are, rely on interpreting extremely faint and complex spectra. A slight misidentification of a spectral line or contamination from light closer to us could place an object in the wrong epoch entirely. Some researchers urge extreme caution, noting that the environment around a brilliant quasar is chaotic. Its intense radiation can create complicated absorption and emission features in the light, potentially mimicking the signature of a more distant object. They call for independent confirmation using different instruments and methods, a standard but vital step in the scientific process. This is not doubt for doubt's sake, it is the essential engine of science. Extraordinary claims, like the existence of a structure that defies the cosmological principle, demand extraordinary evidence. The teams behind the giant arc and the Godzilla Galaxy know this. They welcome the scrutiny because each challenge makes the evidence stronger or reveals a hidden flaw. This back and forth is how science cautiously approaches a potential revolution. It is a collective effort to ensure we are not just seeing patterns in the clouds, but mapping the true foundations of the cosmos. The invisible hand that shapes all galaxies might hold the ultimate answer. To truly grasp the Godzilla Galaxy's impossible size, we must look past the glowing gas and brilliant stars to the dark, silent scaffold that holds it all together. In the lambda-cold dark matter model, the formation of every structure, from the smallest dwarf galaxy to the largest supercluster, begins not with visible matter but with dark matter. After the Big Bang, dark matter, responding only to gravity, began to clump first, forming vast, diffuse clouds called halos. These halos are the cosmic attractors, the gravitational pits that draw in the ordinary hydrogen gas. The gas then cools, condenses, and eventually ignites into the stars we see. The size and maturity of a galaxy are therefore dictated by the size and age of its dark matter halo. This presents the core puzzle of Mammoth 1. For it to host such a massive, active galaxy and a burgeoning cluster so early, its dark matter halo must have been colossal and fully formed when the universe was shockingly young. According to standard lambda-cold dark matter simulations, halos of that scale simply should not have existed yet. They needed more time to gravitationally gather from the smooth background of the early cosmos. So the question becomes, did the Godzilla Galaxy just get improbably lucky, landing in the one in a trillion earliest massive halo? Or does its existence hint that our understanding of dark matter itself needs a revision? This is where theoretical physicists step in, proposing tweaks to the dark matter recipe that could allow for faster, earlier clustering. One intriguing idea is warm dark matter. In the standard model, dark matter is cold, meaning its particles move slowly, which allows them to clump easily into small structures that then merge into larger ones. Warm dark matter, by contrast, would consist of particles moving at higher speeds. This subtle difference has a dramatic effect. That extra motion would smooth out the smallest clumps, suppressing the formation of the tiniest dwarf galaxies in the early universe. But paradoxically, it could allow the larger filaments and halos of the cosmic web to form more quickly and prominently. It would be like changing the consistency of the universe's batter from a fine flour to a coarser cornmeal. You get fewer tiny lumps, but the biggest structures can set up faster. Another possibility is self-interacting dark matter. In the standard view, dark matter particles are aloof, passing right through each other without a glance. But if dark matter particles could interact with each other through some unknown force, even weakly, it would change the physics inside the halos. This interaction could transfer energy, smoothing out the dense cores of halos and potentially making it easier for them to merge and grow massive more rapidly. Both of these concepts are departures from the simplest version of lambda-cold dark matter, but they are not wild guesses. They are serious attempts to reconcile the model's overwhelming successes with stubborn anomalies like the Godzilla Galaxy. The glowing gas we see with ALMA, the furious quasar, the sprawling stellar nurseries, all of these are just the visible symptoms. The real disease, or rather, the real architectural marvel, lies in the unseen gravitational depths. The Godzilla Galaxy may be the first clear signpost pointing toward a richer, more complex nature for the most abundant substance in the universe. But this is more than just a structural oddity, it is a fossil. The Godzilla Galaxy is a cosmic ruin from the dawn of time, a relic so ancient it lets us perform archaeology on the universe's infancy. When an archaeologist digs up a shard of pottery or the foundation of a temple, they are not just looking at an object, they are reading a story written in clay and stone. They can infer trade routes, social hierarchies, and technological prowess. In the same way, astronomers are now sifting through the light from Mammoth 1, searching for chemical fingerprints that tell the story of the universe's first generations. One of the most critical clues lies in its chemical composition. The very first stars in the cosmos, known as population 3 stars, were behemoths made almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. They lived fast and died young in colossal supernova, and in their violent deaths they forged the first heavy elements like carbon, oxygen, and iron, and scattered them into space. These elements became the building blocks for rocky planets and for life itself. So when we analyze the Godzilla Galaxy, a key question arises: is its gas enriched with these heavy elements, or is it still relatively pristine? If its halo shows significant metal enrichment, it would be a sign that this titan formed in a region that had already seen multiple generations of frantic star formation and death, a cosmic metropolis that got a very early start. If, however, the gas is more primordial, it might suggest we are seeing a structure that formed from unusually pure, undisturbed rivers from the cosmic web, a giant built from virgin material. Ultra-keen eyes can detect the faint spectral lines of molecules like carbon monoxide within the gas cloud. The presence and abundance of such molecules are direct traces of past stellar activity. Each measurement is like carbon dating a cosmic artifact, placing it within a timeline of chemical evolution. This galaxy is not just a monster, it is a unique time capsule. We have very few windows into the universe's first few billion years, an era shrouded in what astronomers call the cosmic dark ages and the subsequent epoch of reionization. Observing a structure as massive and active as Mammoth 1 from that time is like finding a perfectly preserved city from a civilization we thought only existed in fragments of myth. It holds answers to questions we are only beginning to ask. How quickly did the first heavy elements pollute the cosmos? Did giant galaxies like this one play an outsized role in ending the universe's dark ages by flooding space with ultraviolet light? Every photon we collect from this distant giant is a message in a bottle, sent 10 billion years ago, and it is telling a story far stranger than our standard models ever imagined. The universe has never been short of record breakers, but even among giants, the Godzilla Galaxy stands apart. Take the hyperluminous quasar RJ1342 plus 0928, a black hole powering the most distant quasar we know. It is stunningly ancient and bright, a beacon from the universe's first 700 million years. Yet it is fundamentally a brilliant point source, a single, furious engine. Mammoth 1 contains such an engine, but it is so much more. It is the entire industrial complex, the glowing gas cloud, the stellar nurseries, and the gravitational hub of a future metropolis all in one. Then consider immense structures like the Saraswati supercluster, a modern-day titan in our cosmic backyard containing thousands of galaxies. Its scale is mind-bending, but it is a mature, fully assembled city, the product of over 10 billion years of mergers and growth. The Godzilla Galaxy is the blueprint for such a city, discovered at the construction site when the universe was a quarter of its current age. Its existence suggests that the blueprints for cosmic cities were drawn far earlier than we ever believed possible. Even among its own kind, the class of objects known as Lyman alpha blobs, Mammoth 1 is an outlier. Other giant blobs glow mysteriously in the distant universe, but few are so clearly anchored to both a brilliant quasar and the nexus of a vast cosmic web filament. This is the trifecta that makes it a singular cosmic monster. It combines an immense cold gas reservoir visible to ALMA, a direct gravitational link to a large-scale structure in the giant arc, and an impossibly early epoch of formation. Each of those features exists elsewhere, but finding all three in one place at that time is what breaks the mold. It is not just the largest, the brightest, or the oldest. It is the earliest evidence of a fully operational cosmic metropolis under construction, a preview of the universe's future architecture playing on a screen from its deepest past. This unique combination is why it does not just add to our catalogue of wonders, it demands a rewrite of the catalogue's very introduction. So how do we test these revolutionary ideas against the cold, hard rules of reality? We build a universe in a box, across the world in supercomputing centers. Cosmologists feed the laws of physics into lines of code and set them running. These are cosmological simulations, virtual universes born from the equations of lambda cold dark matter. They start with a smooth, hot soup of particles at the moment of the Big Bang, apply the known forces of gravity, dark matter, and dark energy, and then let the clock run forward for billions of virtual years. The goal is to see if, by following our established rules, the computer can spontaneously grow structures that match what we actually see when we point our telescopes at the sky. It is the ultimate test for our theories, and when it comes to the epoch of the Godzilla Galaxy, the simulations paint a very specific and very different picture. They show a young universe that is indeed beginning to clump, but in a gentle, gradual way. You would see faint, wispy filaments of the cosmic web starting to condense, dotted with many small, young protogalaxies. The occasional larger protocluster might be beginning to form, but it would be a loose, amorphous gathering, not a dense, shining metropolis under construction. The structures would be modest, growing slowly from the bottom up, exactly as the standard model predicts. Now, take that simulated snapshot and place it side by side with the actual observational data of Mammoth 1 and the giant arc. The discrepancy is not subtle, it is staggering. On one side, a theoretical early universe of scattered villages and faint country roads. On the other, the observed reality, a gleaming, half-built megalopolis centered on a billion solar mass black hole, all connected by a superhighway of gas and galaxies spanning billions of light years. The Godzilla Galaxy is not just an outlier, it is an architectural marvel that appears in the wrong century of the cosmic timeline. This visual clash forces a critical and uncomfortable question upon scientists. Is the problem with the power of our simulations, or is it with the physics we are feeding into them? One possibility is that we simply need bigger, more detailed simulations. Perhaps the virtual boxes we use are still too small to capture the rare, extreme peaks in the density of the early universe where a Godzilla galaxy could form. It is like trying to predict the weather patterns for an entire continent with a model that only covers a single state. You might miss the once-in-a-century hurricane. Running simulations with higher resolution and larger volumes is a constant, demanding race for more computing power, and it could yet reveal that monsters like Mammoth 1, while rare, are possible within standard physics. But the other, more profound possibility is that the simulations are faithfully following the rules, and the rules themselves are incomplete. The inputs, the physics of lambda cold dark matter, might be missing a crucial ingredient. This is where the tension becomes a catalyst for discovery. The Godzilla Galaxy stands as a cosmic benchmark, a data point that future simulations must now strive to hit. Any new proposal for warm dark matter, self-interacting dark matter, or exotic initial conditions must prove itself by successfully growing a Godzilla in the virtual young universe. It transforms the mystery from an abstract puzzle into a concrete engineering challenge for our models of reality. The simulations are not just tools, they are the proving grounds for the next revolution in cosmology. Its ultimate fate is written in the laws of gravity. If we could project forward 10 billion years from its youth to the present cosmic day, the frantic construction site of Mammoth 1 would have settled into a finished, terrifyingly grand metropolis. The Godzilla Galaxy will not remain a lone titan. Over eons, its immense gravitational pull, anchored by that monstrous dark matter halo, would have acted as a cosmic magnet. It would have drawn in hundreds, perhaps thousands of other galaxies from along the filaments of the giant arc. They would have spiraled inward, merging and being cannibalized in a slow, violent dance. The brilliant, gas-rich quasar at its heart would have eventually consumed its available fuel, quieting down. The furious starbursts would have subsided, their gas supply exhausted. What would be left is the dense, red and dead core of a supergiant elliptical galaxy, a behemoth containing the combined mass of all its conquests, floating in a sea of ancient stars. This would become the brightest cluster galaxy, sitting at the gravitational center of one of the most massive structures in the modern universe, a cluster rivaling the Great Coma cluster we see today. Picture the Coma cluster, a swarm of over 1,000 galaxies bound together, so dense that from within it, the night sky would be littered with the soft glow of neighboring galaxies. That is the future of the Godzilla Galaxy. The vast ocean of cold gas observed by ALMA would have long since been converted into stars or stripped away in collisions, leaving a hot, thin plasma between the galaxies glowing in X-rays. The entire system would be dominated invisibly by the same dark matter scaffold that allowed it to form so quickly, now grown into an almost unimaginably massive gravitational well. This narrative arc from violent infant to stately elder giant completes the story but deepens the mystery. It means that somewhere in the cosmos right now, there likely exists a galaxy cluster of extraordinary mass whose core was already a bustling city when the universe was in its infancy. We may have already seen it with our telescopes and not known its incredible history. It forces us to look at the largest structures in the present-day universe with new eyes, wondering which of them were the rule-breaking monsters of the dawn of time. The key to unlocking this mystery may already be on its way. The James Webb Space Telescope has turned its golden eye toward the Godzilla Galaxy, and its unique vision could provide the breakthrough answers we desperately need. Why is Webb the perfect tool for this job? It all comes down to light and time. The light from Mammoth 1 has been traveling for over 10 billion years. The expansion of the universe has stretched that light tremendously, shifting it from the visible and ultraviolet wavelengths it was emitted in, all the way into the infrared part of the spectrum. Our eyes cannot see infrared, and most ground-based telescopes struggle with it because Earth's atmosphere glows brightly in these wavelengths. The James Webb Space Telescope, however, was built for this. Orbiting beyond our atmosphere with a massive gold-coated mirror tuned to catch infrared light, it is essentially a time machine designed to see the earliest epochs of the universe with crystal clarity. For the Godzilla Galaxy, Webb is not just another telescope, it is the ultimate cosmic detective, equipped to see details we have only guessed at. So what exactly will it look for? First and foremost, it will hunt for the fingerprints of the very first stars. Webb's powerful spectrographs can analyze the faint infrared glow from the galaxy's halo, searching for specific chemical signatures. If the gas shows an extreme lack of heavy elements, it would be strong evidence that the Godzilla Galaxy is being fueled by pristine material, and that we might be witnessing the aftermath of those mythical first-generation stars, the population 3 giants. Finding their chemical legacy would be a monumental discovery, like uncovering the fossilized bones of the very first animals on Earth. Secondly, Webb can pinpoint the exact power source of that immense glowing halo. Is the light coming from the furious quasar at the center, from rampant star formation throughout the cloud, or from the violent infall of cold gas? Webb's sharp infrared vision can map the distribution of different types of emission across the blob, effectively creating a heat map of the energy. It could show us if the quasar's radiation is flooding the entire structure like a lighthouse beam, or if there are pockets of intense starlight glowing independently. This would finally answer what engine drives this cosmic monster. Perhaps most excitingly, Webb will give us our first truly sharp view of the galaxy's structure. Ground-based observations and even ALMA amazing data show us a colossal, fuzzy smudge of light and gas. Webb's incredible resolution will cut through that fuzziness, potentially resolving individual giant star-forming regions within the cloud, or revealing the intricate, filamentary streams of gas flowing into the core from the cosmic web. It will show us the monster's anatomy. Is it a single, chaotic entity or a collection of several massive galaxies in the process of merging? Webb's images could settle that question, showing us the Godzilla Galaxy not as a blurry mystery, but as a detailed portrait of cosmic construction in overdrive. Every new piece of data from Webb will be a crucial clue, feeding back into the supercomputer simulations and refining our models of dark matter and cosmic evolution. This is the next step in the investigation. We have found the crime scene, identified the suspect, and now we are bringing in the most advanced forensic equipment in history to examine the evidence. What Webb reveals about this one distant titan could rewrite the opening chapter for every galaxy in the sky. This single discovery forces us to reconsider the origin story of every galaxy in the sky. For decades, the textbook narrative of cosmic growth has been one of patience and gradual assembly. It is a bottom-up story. Tiny clumps of dark matter and gas slowly coalesce into the first small galaxies. These galactic building blocks then spend billions of years merging, crashing together, and cannibalizing one another to build the majestic spirals and giant ellipticals we see today. It is a tale of cosmic Legos piecing together a universe from the smallest bricks upward. The Godzilla Galaxy does not just add a larger Lego block to this story. It suggests an entirely different construction manual was at work in the early universe. It points to a top-down process where vast, pre-existing sheets and filaments of the cosmic web structures already spanning billions of light years could collapse under their own immense gravity all at once. In this scenario, a colossal structure like Mammoth 1 isn't the end product of many mergers, it is the starting point. Imagine the difference between building a city by first constructing individual houses and then grouping them into neighborhoods versus finding a fully planned metropolis with its skyscrapers and highways already laid out in a single, rapid blueprint. The early universe might have been capable of both methods simultaneously. This isn't a minor tweak, it is a fundamental shift in perspective. If true, it means the cosmos got a head start on its largest projects, laying down the frameworks for future superclusters while it was still furnishing its first small galaxies. The implications ripple outward, touching every aspect of galaxy evolution. Our estimates for star formation rates in the early universe may be far too conservative. We thought the first galaxies were modest and slow to ignite. But if top-down collapse was common, it could have triggered ferocious, widespread bursts of star formation almost immediately, flooding the young cosmos with light and heavy elements much faster than our models predict. The timeline of the cosmic dawn, that pivotal era when the first stars ended the universe's dark ages, may need to be moved dramatically earlier. Similarly, the growth of supermassive black holes becomes an even more urgent puzzle. Our bottom-up models struggle to explain how billion solar mass monsters appeared so quickly. But if those black holes were sitting at the dense nexus of these rapidly collapsing cosmic web filaments, they would have had a vast, pre-organized buffet of gas delivered directly to their doorstep. They weren't slowly growing in isolation. They were born into a position of extreme privilege at the center of a gravitational avalanche. This changes the narrative from one of gradual cultivation to one of instant, violent feasting. The very classification of galaxies might need refinement. We categorize them by shape: spiral, elliptical, irregular. But if a significant population of early giants formed through this rapid top-down channel, their shapes, their chemical compositions, and their internal structures could carry the signature of that violent, monolithic birth, distinct from galaxies built purely through later mergers. Textbooks would need a new chapter, one that acknowledges a more chaotic and accelerated infancy for the cosmos, where the rules of construction were not as orderly as we once believed. The universe, it seems, was not just a careful craftsman. It was also a daring architect willing to sketch entire cities in a single, breathtaking stroke. That unsettling question forces us to confront a bedrock assumption of modern science. The cosmological principle is not just a convenient idea, it is the philosophical cornerstone upon which we have built our entire picture of the universe. It states that, on the largest scales, the cosmos is homogeneous and isotropic. In simple terms, no matter where you are or which way you look, the universe should appear roughly the same. There should be no center, no edge, and no gigantic, unique structures that make one region fundamentally different from another. This principle is what allows us to do cosmology at all. It lets us assume that the laws of physics we measure here are the same everywhere, and that a snapshot of one vast volume of space is a reasonable representation of the whole. It is the ultimate declaration of cosmic mediocrity, the idea that our vantage point is utterly ordinary. But what if the giant arc is real? A coherent structure spanning 1/15 of the observable universe is the precise opposite of homogeneity. It is a feature, a pattern, a direction. It suggests that if you were standing in a galaxy within the arc, your view of the cosmos would be fundamentally shaped by this immense backbone of matter. Your night sky might be streaked with the glow of a nearby filament, a celestial river of galaxies so vast it defines your entire cosmic neighborhood. From that vantage point, the universe would not look the same in all directions. One axis would be special. This is not a minor tweak to a theory, it is a philosophical earthquake. It challenges the very notion of a universe without preference. For centuries, since Copernicus moved us from the center of the solar system, science has consistently dethroned us from positions of specialness. We orbit an average star in an unremarkable part of a common galaxy. The cosmological principle was the final step in that demotion, placing our entire galaxy in a featureless cosmic expanse. But if the universe itself has a grain, a large-scale texture with filaments and voids on scales we are only beginning to map, then the definition of ordinary changes. We may not be at the center, but we might exist within a local texture that is not representative of the whole. Our entire observable universe, the sphere of space 14 billion light-years in radius that we can see, might itself be just a single sample of a far grander and more varied structure. This realization carries a profound existential weight. For generations, the vast, uniform emptiness of space has been a source of both awe and existential dread, the feeling of our terrifying smallness in an indifferent void. But a textured, structured universe, one with architecture on the grandest scales, replaces that indifferent void with something else, a cosmic landscape. We are not adrift in a featureless ocean. We are within a continent, part of a geography whose full map we cannot yet see. This shifts our place from being a random speck in a uniform sea to being an inhabitant of a specific neighborhood in an immeasurably vast and complex cosmos. It does not make us central, but it does make our context rich, specific, and potentially rare. The search for understanding becomes not just about universal laws, but about cosmic geography. Are we in a dense filament, a sparse void, or on the shore between them? And what does that environment mean for the history of our own galaxy, or the potential for life elsewhere? The Godzilla Galaxy is more than a scientific anomaly. It is a signpost pointing toward a universe far more intricate, patterned, and strangely beautiful than our simplest principles dared to suggest. When the team's research paper landed in the Astrophysical Journal, it sent immediate shockwaves through the scientific community, but the story did not stay within the halls of academia for long. Within days, the Godzilla Galaxy had burst into the public consciousness, splashed across news sites and science magazines with headlines designed to stun. They called it the Monster Galaxy, the Cosmic Titan, the behemoth that breaks physics. That nickname, Godzilla, proved irresistible, perfectly capturing the scale and the disruptive power of the discovery. It was not just another distant smudge, it was a character, a colossal entity with a name that evoked both awe and a touch of cinematic dread. Social media lit up with artists' impressions, depicting the swirling vortex of gas and light, often with a sense of mythical scale that made our own Milky Way look like a pebble beside a mountain. The public's fascination was instant and profound. Why does a discovery like this, rooted in complex data about redshift and dark matter halos, grip us so powerfully? It taps into something far deeper than simple curiosity. At its heart, this is a story about a rule breaker, an outlier that defies the established order. We are instinctively drawn to anomalies, to things that do not fit. They represent mystery, and mystery is the engine of all exploration. A galaxy that challenges our fundamental models of the universe is not just a scientific problem, it is a narrative hook, a plot twist in the greatest story ever told, the story of everything. It rekindles that childlike sense of wonder about the night sky, transforming it from a static tapestry of stars into a dynamic, unfinished, and deeply strange construction site. We look up and are forced to admit with a thrilling humility that we do not have it all figured out. There are still monsters in the dark, and they are forcing us to redraw our maps of reality. This public frenzy is more than just media hype. It is a reflection of our innate desire to explore and to understand our place in the cosmos. Every time a discovery like the Godzilla Galaxy emerges, it is a reminder that the universe is still capable of surprising us, of presenting puzzles that humble our intellect and ignite our imagination in equal measure. The human story behind the data is often where the real drama unfolds. To get that perspective, I reached out to one of the lead researchers on the team, and while this is a recreation of our conversation, it captures the genuine spirit of discovery. The first thing I asked was about the moment they knew they had found something extraordinary. The researcher's voice was still charged with the memory. "You have to understand," they said, "we weren't looking for a monster. We were meticulously mapping faint emissions from cold gas in a specific EarlyUniverse survey field. The data from ALMA came in, and we began building up the image pixel by pixel. Most sources appear as small, faint blobs, but this one, it just kept growing. The software kept mapping it, and the structure on our screens didn't stop. It grew larger and brighter and more complex. We kept checking for errors, for calibration issues, anything that could create a false signal of that scale. But it persisted. That was the first heart-pounding moment, seeing a shape emerge in the data that was an order of magnitude larger than anything else in the field. It wasn't a eureka shout. It was a stunned silence around the room, followed by a frantic, whispered, "What is that?" The challenge then shifted from detection to comprehension. The researcher described the analysis phase as a marathon of doubt and verification. The redshift measurement was the linchpin. We had this glorious gas cloud from ALMA, but to prove its age and distance, we needed the spectroscopic fingerprint from the optical telescopes. Getting a clean spectrum from something that distant and faint is like trying to hear a whisper in a hurricane. The light is incredibly faint, and the atmosphere itself creates noise. When the first spectrum from the Subaru telescope was processed, and we saw that Lyman alpha line dramatically redshifted, confirming the distance, that was the second huge wave of validation. But then the real work began, the statistical battle. We had to prove to ourselves and to every skeptical peer in the world that the giant arc was not a chance alignment. That involved months of running probability simulations, of testing our algorithms against mock skies, of trying to break our own discovery. It's a deeply uncomfortable but essential process. You fall in love with your finding, and then you have to try to kill it with every tool you have. Only if it survives that onslaught can you truly believe it. I asked about the personal weight of challenging something as foundational as the lambda cold dark matter model. The researcher paused, choosing their words carefully. It's a profoundly mixed feeling. On one hand, there's a thrilling sense of being at the very edge of the map, of seeing something no one has seen before. That's why any of us do this, but on the other hand, lambda CDM isn't just some theory, it's the framework. It's the backbone of modern cosmology. It has predicted so much so accurately. To have data that seems to strain against it is intimidating. You start questioning your own work before anyone else does. Could we have made a mistake? Did we miss something? The idea that we might be pointing toward a need for new physics is not something any scientist takes lightly. It feels like being a carpenter who has used a trusted level for decades, only to take a measurement that suggests the level itself might be warped. You check your measurement 100 times before you even consider the tool might be wrong. Ultimately, they said, this is how science progresses. It's not a steady, stately march. It's a series of stumbling steps, often in the dark, guided by these strange, luminous anomalies that refuse to fit. The Godzilla Galaxy is that for us. It's not an indictment of the old models, but a demanding question they cannot easily answer. It forces everyone to look harder, think deeper, and build better tools. That pressure is what creates progress. The most exciting part isn't having an answer, it's living in the question, and knowing that whatever the solution is, it will reveal a universe even more astonishing than the one we thought we knew. Of course, we have to address the giant radioactive elephant in the room. Let's have a little fun and clear up what the Godzilla Galaxy absolutely is not. First and foremost, this cosmic titan is not a threat to Earth. It is not stomping through the cosmos, heading our way to swat our little blue planet out of the sky. The distance alone makes that impossible. We are seeing it as it was over 10 billion years ago, and in the vast expansion of the universe since that light left, it is now impossibly far away, receding from us at a speed we can scarcely comprehend. It exists in a different part of the cosmic ocean altogether, a distant continent we are only now glimpsing from our island shore. It is also not alive. It doesn't have thoughts, desires, or a consciousness. The monster metaphor is just that, a metaphor we use to grasp its scale and its rule-breaking nature. It is a collection of gas, dust, stars, and dark matter governed by the impersonal laws of physics. There is no cosmic brain in there plotting galactic domination. And while we call it a galaxy, it's crucial to understand the sheer scale difference between a galaxy and our own home system. Our solar system is our immediate neighborhood. It is our sun, the planets, asteroids, and comets all bound by its gravity. You could fit our entire solar system, from the sun to the distant Oort cloud, inside a tiny, insignificant speck within the Milky Way. A galaxy, on the other hand, is the entire city. It is a vast island of hundreds of billions of stars, all orbiting a common center of gravity, along with all their planets, nebulae, and black holes. The Godzilla Galaxy is not just a city, it is the blueprint for a future metropolis of such cities. So while the name is thrilling and evocative, remember it's a nickname born from awe, not a literal description. It's a monster of scale and mystery, not of flesh and fury, and its real story is far more fascinating than any simple sci-fi plot. This immense story of cosmic discovery does not belong only to professional astronomers in their remote observatories. It belongs to anyone who has ever looked up at the night sky and wondered. In fact, you can be a part of this grand project of cosmic exploration right now from your own home. Across the globe, a revolution in citizen science is unfolding. where the collective curiosity of the public is helping to sift through the mountains of data that modern telescopes produce. Platforms like Zooniverse host projects where volunteers, people just like you, can help scientists classify galaxies, search for distant supernova, or even identify the subtle signatures of asteroids. Imagine the data from a sky survey containing images of millions of galaxies. No single research team could possibly examine each one in detail, but by distributing the task to thousands of eager eyes online, patterns emerge and rare objects, perhaps even the next Godzilla Galaxy, can be flagged for further study. Your careful click could be the one that leads to the next great mystery. For those with a telescope, the story is even more direct. While you cannot see the Godzilla Galaxy itself from your backyard, you can train your lens on the regions of sky being studied by the great observatories. You can follow the announcements from space agencies like NASA and the European Space Agency, and then go out and look toward that patch of darkness, knowing that the light from such profound mysteries is passing right through your eyepiece, a connection across 10 billion years. This active engagement transforms the experience from passive watching into active participation. It fosters a powerful sense of community, a shared endeavor to map the cosmos. Every time you read an article about a new discovery, share it with a friend, or simply step outside to gaze at the stars, you are participating in the oldest and grandest of human traditions, the search for our place in the universe. The story of the Godzilla Galaxy is not finished. New data from the James Webb Space Telescope will arrive, new simulations will be run, theories will be challenged and refined. And you can be there for every step, a citizen of the cosmos, staying curious and connected as the greatest story ever told continues to unfold in ways we cannot yet predict. The discovery of one cosmic monster inevitably raises a haunting question. Are we looking at a solitary freak of nature, or have we merely spotted the first member of an entire hidden population? The sheer scale of the cosmos suggests the latter. If our standard models are correct, finding a structure as extreme as the Godzilla Galaxy should be a 1 in a trillion occurrence. But the universe is so vast, containing potentially 2 trillion galaxies, that even 1 in a trillion odds could still mean there are thousands of such monsters lurking in the darkness, waiting to be found. The real issue is not their potential existence, but our ability to see them. Until now, our deepest surveys have been like shining a flashlight into a cavern, illuminating only a tiny, specific patch of the cosmic wall. We have been peering through keyholes, not opening doors. That is all about to change with a new generation of telescopes designed not to stare deeply at one spot, but to scan the entire sky with unprecedented speed and sensitivity. The champion of this new era is the Vera-C Rubin Observatory, currently under construction in Chile. Its core mission is the Legacy Survey of Space and Time, or LSST. This is not an incremental upgrade, it is a revolution in perspective. Over 10 years, its enormous mirror and giant camera will photograph the entire available sky every few nights, creating a dynamic, living movie of the cosmos. It will not just see billions of galaxies, it will watch them change, detecting subtle shifts in brightness and position that reveal their secrets. For the hunt of cosmic monsters, the LSST is a game changer. Its wide field of view means it will systematically comb the entire celestial sphere, leaving no dark corner unexamined. Its incredible sensitivity will allow it to see faint, diffuse structures like the glowing halos of distant Lyman alpha blobs. Most importantly, by repeatedly scanning the same areas, it can use a powerful technique called gravitational lensing to map the invisible. When light from a distant galaxy passes near a massive object like the Godzilla Galaxy, its path is bent, distorting and magnifying its image like a funhouse mirror. By studying these subtle distortions in the shapes of millions of background galaxies, the LSST can effectively weigh the dark matter halos of foreground structures, revealing the true mass distribution of the early universe. It will find the gravitational shadows of giants, Astronomers estimate that surveys like the LSST could uncover not dozens, but hundreds of candidates for extreme protoclusters and giant arcs from the universe's first few billion years. Each one would be a new data point, a new piece of evidence in the trial of our cosmological models. If we find that Godzilla galaxies are exceedingly rare, it might allow us to tweak lambda cold dark matter to accommodate a few statistical outliers. But if we find they are common, if the early universe is teeming with such prematurely massive structures, then no tweak will suffice. We will need a fundamental rewrite. The question then shifts from whether our models are incomplete to a more profound inquiry. What if our entire conception of the universe's infancy is a gentle fiction? We have long pictured it as a calm, slowly simmering soup. But what if it was a roaring, turbulent cauldron where colossal waves of density crashed together almost immediately, seeding giants from the very first moments? The answer is written in the sky, in the faint light of 10-billion-year-old monsters. We have only just begun to read their story. 3 immense puzzles now stand between us and a complete understanding of this cosmic titan. The first is the timeline problem. Mammoth 1 is simply too colossal for its age. According to our best models, a structure of this scale, a bustling protocluster, should not have had the billions of years necessary to gather its immense mass when the universe was a mere toddler. Its existence suggests a construction process that was shockingly fast, a cosmic shortcut we have not yet mapped. The second is the structure problem, embodied by the giant arc. This filament of galaxies and gas, spanning a staggering 3.3 billion light-years, directly challenges the cosmological principle, the foundational idea that the universe should look roughly the same in all directions on the largest scales. Finding such a coherent, immense pattern so early is like discovering a mountain range that stretches across an entire continent on a world that was supposed to be perfectly smooth. The third and final puzzle is the power problem. What possible engine could illuminate the galaxy's vast, glowing halo of hydrogen gas? Is it the furious radiation from a billion solar mass black hole, a frenzy of star formation of unimaginable intensity, or the violent crash of cold gas rivers from the cosmic web? Each potential answer points to a system operating at extremes we struggle to explain. These 3 challenges are not separate issues. They are intertwined threads of a single, deeper mystery, forcing us to question the very blueprints we use to build our universe in theory. The timeline problem asks how it grew so fast. The structure problem asks where it found the material. And the power problem reveals the violent processes that such rapid, immense growth inevitably unleashes. Together, they form a perfect storm of contradiction, a cosmic anomaly that refuses to fit neatly into our existing catalogue of knowledge. This is the legacy of the Godzilla Galaxy, a beacon from the dawn of time that illuminates not just ancient gas, but the profound gaps in our understanding of everything. The Godzilla Galaxy is not merely a champion of cosmic superlatives, a trophy for the record books. It is a living question, a single point of light that has become a catalyst for a quiet revolution in how we see the cosmos. Its existence pushes at the very boundaries of our knowledge, forcing us to hold our most fundamental theories up to the light and examine them for cracks. We built a magnificent model of the universe, elegant and predictive, and then we found a monster from the dawn of time that does not fit inside it. That tension is not a failure of science, it is science in its purest, most vital form. It is the universe speaking back, correcting our assumptions, and demanding a deeper, more nuanced story. This distant giant reminds us that our maps of reality are always provisional, always being redrawn by the next astonishing discovery just over the horizon. And that horizon is about to expand dramatically. The final chapters of this mystery are not yet written. They are being written right now in the fresh data streaming down from the James Webb Space Telescope, in the hum of supercomputers running new simulations, and in the collective curiosity of astronomers around the globe. So this is an invitation, not an ending. Stay tuned. Watch the skies, both figuratively and literally. Follow the announcements, marvel at the new images, and keep looking up at the night sky with that sense of wonder. Embrace the beautiful, humbling mystery of a cosmos that is far stranger and more wondrous than we ever dreamed. A universe that still has magnificent monsters lurking in its dark, uncharted corners, waiting to teach us how little we truly know.